Hello, welcome to this screencast, which is a continuation of one from before on the membrane potential. So we're looking here now in this one to actually explain how the membrane potential is established and then also maintained. So from a previous screencast, we had discussed what it means to be polarized and the fact that the neuron is a polarized cell and that there's a difference across the membrane that we're showing measured down here by the with the oscilloscope. So I want to talk about how that actually happens. And so one of the main players in that is, of course, the sodium-potassium pump. So this is the sodium-potassium pump, and it is a pump because it is moving 3 sodium ions out and 2 potassium ions in, and it's moving these things against their concentration gradient. So when we have a pump, again, we are using this energy ATP here to go against the concentration gradient. So because you have these sodium-potassium pumps in the membranes of the neurons, what you see happening here is, of course, you're moving these 3 sodium ions out. There's 1, 2, 3 that are getting pumped out, right? And so we have 3 positive charges being moved out, and that is constantly happening. And then when this sodium-potassium pump changes its conformation, and so it goes to here, to here, to here, it's moving those 3 sodiums out, and then it's, of course, moving 2 potassiums in. Right? Now, how do we get then the difference? Well, the difference is that the outside is positive, the inside is negative. And from before, we discussed that negative, actually, another way of saying that is less positive. And so I think now you may be able to see why the inside is less positive, because we're moving 3 positives out, but then only moving 2 positives back in. Right? So 3 out, 2 in. The difference is going to be that we have more positive on the outside and less positive on the inside. Right? And so this sodium-potassium pump is constantly working to help establish this gradient, that we get these sodium ions on the outside, right? Potassium ions high in concentration on the inside. Right? So the overall net effect, again, is that we have, so the concentration of sodium ions on the outside is relatively high compared to the concentration of sodium ions on the inside. So the concentration gradient for sodium right here favors the movement of sodium back into the cell. But of course, that doesn't happen because of this polarized membrane right here. These hydrophilic heads do not allow these sodium ions to diffuse back across, but this pump is actually pumping them across, making that gradient. The same is happening for potassium, but just in the opposite direction. Right? These potassium ions end up inside the cell at a higher concentration. So the concentration of potassium ions is higher inside the cell with respect to potassium outside the cell. So the tendency will be for these potassium ions to diffuse out, but they won't because of this hydrophilic membrane right there, or those hydrophilic heads on the membrane right there. So the concentration gradient for potassium, right, favors potassium diffusing out, but of course it won't, again, because of the membrane. So this sodium-potassium pump is always constantly working there to help maintain and establish that difference across the membrane. In addition to that, the story gets a little bit more complex in that we have sodium channels and we have potassium channels. So sodium ion channels and potassium ion channels exist in the membrane and help to establish and maintain a resting membrane potential. So in purple here, these are the sodium channels. And you notice that these sodium channels here, so this is a sodium channel, and this is a sodium channel, and this is a sodium channel. And so you notice that these sodium channels here are closed, right, at rest. And these sodium channels are voltage sensitive. The gates on them are voltage sensitive. And so when the charge inside the cell is negative 70 millivolts, these sodium channels are closed. So we've got these several sodium channels all throughout the membrane of the neuron. We also have potassium channels. So these are for potassium right here. And you notice that these are closed, right? And these are potassium ones that are closed, and these are potassium ones that are closed. Right? And again, they're also voltage sensitive. So at minus 70 millivolts, these, and the charge is negative 70 millivolts inside the cell here, these potassium channels are closed. But you do have some potassium channels here that are open regardless of what the regardless of what the charge is inside the cell. And so in this case, these potassium channels, right, are what are known as leaky channels. Right? So these are the leak channels for potassium. And these are open regardless of the charge over here inside the cell. And so what's happening is, why do we see these potassium ions diffusing out of the cell? Well, the answer is because of these potassium, as you know from the previous slide, potassium's in high concentration inside the cell. This is supposed to be an up arrow. Potassium's in high concentration inside the cell. Why? Because over here, the sodium-potassium pump is moving potassium in constantly against its gradient and establishing potassium high on the inside there. And so the tendency will be for potassium to diffuse out. Right? Will it diffuse across the membrane here? No, it doesn't, but this channel is open, so the potassium ions diffuse out. So subtly, if you are paying attention here, what you might notice is that potassium diffusing out, well, since the potassium diffuses out and it's positively charged, it's taking positive charge with it. So these leaky channels are also contributing to the overall net positive charge on the outside of the cell, and the inside of the cell becoming less positively charged or negatively charged. So not only do we have this sodium-potassium pump over here, so this is one thing that's establishing the resting membrane potential of positive on the outside, right, and negative on the inside, or less positive on the inside. That's one thing. But then the second thing over here are these leaky potassium channels as well. These leaky potassium channels enable some of that potassium to diffuse out of the cell. Right? Will all of it diffuse out? No, because then it's being pumped back in. But what happens is this membrane, right, the charge across the membrane, so I'm looking at, this is the outside, this is the inside. So what's happening is that this comes into a dynamic equilibrium balance, right? Will all of this potassium diffuse out? No, because it's being pumped back in here by the sodium-potassium pump. And so what we end up in the end having established is an electrochemical gradient. We have this electrochemical gradient established across the membrane, where the tendency will be for this potassium to diffuse out. But will all of it diffuse out? No, because it's being pumped back in, but also because as we generate a positive charge out here, right, and a negative charge here, some of that positive is attracted back into the cell here. The negative and the positive attract, and so you balance this this chemical gradient, the concentration gradient, with the electrical gradient here, this attraction of some of that potassium back in, and so this comes into balance here. It's a dynamic balance. I think that if you run the PowerPoint from Blackboard and click on that, this puts it into a dynamic situation here. It shows you an animation of what's going on here that might be a little bit more helpful. Right? So again, what we have going on to establish, or how the resting membrane potential comes into play here, is that we have, oops, I'm going to go back this way. We have the sodium-potassium pump moving 3 sodium out, 2 potassium in. That creates this difference. But then we also have these leaky potassium channels where some potassium is going to be diffusing out, and facilitatedly diffusing out. Right? But not all of it, because then you get this attraction of this back in here. So you have this cycling of these potassium ions here. Right? And again, I think clicking on that will be a little bit better. So again, this is just showing you the whole overall situation here. Again, this negative 70 millivolts. This is the charge inside the cell with respect to outside the cell. Again, this is the reference electrode here. We're measuring the inside. And why is that? It's because we have leaky potassium channels. We have the sodium-potassium pump that is generating this difference across the membrane. Right? positive on the outside, less positive on the inside, or negative on the inside. Okay? So you should be able to here explain how that resting membrane potential is established, right? And then also how it is maintained here. Right? Thanks for listening. Bring your questions to class. See you then.